Hello, welcome to this latest video from iLearn Engineering. I'm going to be doing part 2 of a cantilever beam with a discrete point load. This time we're going to do it with actual numbers in rather than algebraically as last time. So off we go. Let's start by introducing a point load to this beam, cantilever beam here, and we're going to have a load pointing vertically down. This is going to be 5 kilonewtons, and the dimensions of the beam are going to be, well, we're going to have this as 1 meter here, and we'll have this as being 2 meters. Okay, 2 meters. So the total length of the beam is 3 meters. We've got our x coordinate down here, which is measured from the tip going towards the root. And as with my previous example, we will need to take some imaginary cuts. We'll have one here, we'll label that one as cut number 1, and cut number 2 is some arbitrary position here. That's number 2. That's a 2. Right, okay, let's go ahead with the analysis. So if we take the position of the first cut, if we were to do that, we'd end up with a little slither of beam here, and then we would have to introduce our shear forces to maintain equilibrium as a result of that cut, which is the shear force Q vertically upwards and a moment there. And don't forget, this is at position X. So if we were to do that, then we would need to write the equations here to the side. So resolving vertically upwards as being positive, we would have Q is positive, and then that's it, nothing else. So Q equals 0. Similarly, if we take moments as being anti-clockwise as being positive, then the moment at the cut, taking moments about the cut, then the moment is 0. So it's fairly easy, the first one there. Let's scroll down and do the next one. So we're going to consider our cut. If it helps, I can bring this imaginary line down to here so you can see. And then we need to put our coordinates on here, which is that is position X from the tip. And then we have a load of 5 kilonewtons was applied, and that was at position of 1 meter from the end. So I can put the 1 meter in there. And the cut is at position X, which is just an arbitrary position. Let's start with writing our equations. So we resolve vertically upwards, then the shear force Q is up. We've not put it in there, but we need to put it in, don't we? There it is. There's our shear force Q at the cut, and there is our moment M at the cut. So Q is vertically upwards, and then we've got this force 5 kilonewtons. That's minus 5 because it's pointing in the opposite direction. And there's no other forces, and they have to equal to 0 because if you remember from the previous video, this is us summing up the forces in a particular direction, in this case the vertically up direction, and then we say that they have to equal 0 for a static equilibrium because the accelerations are 0. So on the left hand side here, Q minus 5 is us summing up the forces and taking account of the directions with the pluses and minuses, because this is a plus Q, that's a minus 5, and that equals 0. So all of that then implies that Q equals 5, okay, or 5 kilonewtons. And then similarly, if we take if we take moments about the cut with anti-clockwise being positive, then we would have following equations. We would have the moment M, and then let's look. So we've got a force, vertical force 5, and it is at a distance of here. What's this distance here? Well, let's sort of Well, this distance here is x, which is the total distance, minus 1. Okay, meters, if you like. That's the distance. But that distance is important because when the 5 kilonewtons gets multiplied by that distance, which is perpendicular, see, because it's a right angle there, then 5 multiplied by the distance gives you a moment, which counteracts this moment at the cut. So let's write it in there. I can do it in color coded if you like. So it's going to be minus, because it's going to be doing a clockwise moment, so 5, and then multiplied by the moment arm, and all of that is going to equal 0. Okay, so again, just to be clear, all of this bit here on the left hand side, that is us summing up the moments about the cut and setting them equal to 0 for a static equilibrium problem. So if we rearrange that equation, then this implies that the moment at the cut is equal to 5 multiplied by the distance x minus 1, and that gives us our equation. So we've got our 2 equations for the shear force and bending moment at the 2 different cuts. So that enables us then to sketch out the shear force here, Q, in kilonewtons, which is going to be equal to, let's put our little markers on here. So we've got, let's say we've got like this distance here and this distance here, the beam. So, and then let's say that this is sort of, this is sort of X there on our beam. So this is sort of 0 if you like, and then this is at 1 meter, and then this will be 2 meters, and that will be 3 meters at the end. So the shear force is 0 in the first section, as you can see from our first cut, and then when it goes to the left of that force, you see that it jumps up and we get this 5 kilonewtons. So it steps up and gives us this constant value of 5 kilonewtons. Okay, now let's come down and do the same for the bending moment. Let's just sketch our axes. Same thing again, we'll sort of line them up. So this would be the starting point, end of the beam. And we can get rid of that bit if you like. And then we will put on this point here and this point here. Right, and this is going to be our moment, and the units are going to be kilonewton meters in this case. So what happens, or the same thing happens at the start, is that the moment was 0, wasn't it? If you remember here, the moment was 0. So that's the easy bit, we can just put that in there. And then if we inspect our equation, it might be easy if we write it in again. This one here, m equals 5 bracket x minus 1. So that's a linear equation, isn't it? And what we need to do really is substitute in the values at the endpoints. So I would substitute in the value for when the x equals 3, which is the total length of the beam, and that will tell us what the moment is at the root of this beam, the reaction conditions, if you like. So we could say that at x equals 3 meters, then the moment is going to equal 5 into 3 minus 1, okay, which is 5 times by 2, which is going to give us our 10 kilonewton meters. So that will be the value at this point. So we'll put that in there. That's our 10, and it's going to be a linear rise. So that gives us our bending moment diagram and our shear force diagram for a cantilever beam with a point load of 5 kilonewtons.